I'm proud to announce Willow. Willow is Google's newest and most powerful superconducting quantum computing chip, and the next step in our path towards building large-scale quantum computers and exploring their applications.
It would be tempting to look at Google's quantum AI crossing a new scientific milestone and assume that the journey to rewrite physics starts now. But the story is actually much older. In 1874, a respected physics professor looked at one of his brightest students and offered what seemed like sensible career advice. Don't study physics. Almost everything important had already been discovered, he argued. The future would consist of little more than refining measurements and filling in a few remaining gaps. That student was Max Planck. 26 years later, he shattered the very foundations of physics. Now, more than 125 years after Planck introduced the quantum world, Google has crossed a milestone that many physicists once feared might never be possible. This is the latest chapter in one of the greatest scientific adventures ever told, one that could eventually change everything. Physics was finished until one man reinvented the whole field. Google's latest quantum processor, Willow, has reignited a question that scientists have been asking for more than a century. Is our understanding of the world about to change forever? If we travel back roughly 150 years, some of the greatest intellectuals of the time had assumed that humanity had reached the pinnacle of technological prowess, much like how we feel about our society today. In 1874, an ambitious 16-year-old named Max Planck was preparing to study physics at the University of Munich when he sought advice from one of his professors, Philipp von Joly. According to Planck's later recollections, Joly discouraged him from entering the field. Physics, he argued, was nearly complete. The great discoveries had already been made, and what remained was simply refining measurements to a few more decimal places. It wasn't an unreasonable opinion. Isaac Newton's laws had explained motion for nearly 2 centuries. James Clerk Maxwell had unified electricity and magnetism. Across Europe, many scientists genuinely believed nature's deepest secrets had already been uncovered. But Planck wasn't discouraged. "I had no desire to discover new things," he recalled years later. "I wanted only to understand the known fundamentals of physics more deeply." It was a humble ambition. Ironically, that quiet determination would soon dismantle the very foundations of classical physics and transform our understanding of reality forever. The confidence of 19th century physics wasn't limited to one professor. In April 1900, one of Britain's greatest physicists, Lord Kelvin, delivered a lecture titled 19th Century Clouds over the Dynamical Theory of Heat and Light. He argued that physics was remarkably complete, with only 2 clouds remaining on the horizon. Those seemingly minor problems involved the strange behavior of light and the mysterious motion of atoms. They sounded like technical details. In reality, those 2 clouds would become the seeds of relativity and quantum mechanics. Even before Kelvin spoke, reality had already begun refusing to cooperate. In 1895, German physicist Wilhelm Röntgen accidentally discovered X-rays while experimenting with cathode rays in Würzburg, revealing a completely invisible form of radiation capable of passing through human tissue. Just 1 year later, French physicist Henri Becquerel stumbled upon radioactivity after uranium salts mysteriously exposed photographic plates without sunlight. Then, in 1897, J.J. Thomson announced the discovery of the electron at Cambridge's Cavendish Laboratory. Atoms, once believed to be indivisible, suddenly had internal structure. The supposedly complete picture of matter was beginning to fracture. Yet the biggest surprise was still to come. Toward the end of 1900, Planck was wrestling with an embarrassing problem known as blackbody radiation. Classical physics predicted that hot objects should emit infinite amounts of ultraviolet light, a nonsensical result later nicknamed the ultraviolet catastrophe. Desperate to make the equations fit the experimental data, Planck proposed something he considered little more than a mathematical trick. Energy could only be emitted or absorbed in tiny discrete packets, which he called quanta. On December 14, 1900, he presented the idea to the German Physical Society in Berlin. "I was ready to sacrifice any of my previous convictions about physics," he later admitted. He believed he had found a convenient calculation. Instead, he had unknowingly rewritten the rules of nature. The journey to quantum AI computing had begun before anyone realized it. The century-long mystery of quantum reality. Max Planck's quantum hypothesis solved one problem, but it created a much bigger one. His equations matched reality with astonishing precision, yet almost nobody understood why they worked. Quantum mechanics would become the most successful scientific theory ever devised, accurately predicting everything from the behavior of atoms to the operation of lasers and computer chips. The first person to realize the true significance of Planck's idea was Albert Einstein. In 1905, during his famous Annus Mirabilis, Einstein proposed that light itself came in discrete packets of energy, later called photons. It was a radical claim. Since James Clerk Maxwell's work in the 1860s, light had been understood as a wave. Einstein argued that, under certain conditions, it behaved like a particle as well. He used this idea to explain the photoelectric effect, in which light, striking a metal, ejects electrons only if it exceeds a specific frequency, regardless of its intensity. Nearly 2 decades later, Einstein received the 1921 Nobel Prize in Physics for this explanation of the photoelectric effect. The discoveries accelerated at breathtaking speed. In 1913, Danish physicist Niels Bohr introduced a revolutionary model of the atom, proposing that electrons occupy fixed energy levels and can only jump between them by absorbing or emitting specific amounts of energy. It explained why atoms produce distinct spectral lines and became the first successful quantum model of atomic structure. Then, in 1924, French physicist Louis de Broglie stunned the scientific community by suggesting that if light could behave like a particle, perhaps matter could behave like a wave. His hypothesis was confirmed just 3 years later, when electron diffraction was observed experimentally by Clinton Davison and Lester Germer in the United States, revealing that particles once thought to be tiny billiard balls possessed wave-like properties. Then, in 1926, Austrian physicist Erwin Schrödinger introduced his famous wave equation to calculate how quantum systems evolve over time. Almost simultaneously, German physicist Werner Heisenberg developed matrix mechanics and in 1927 formulated the uncertainty principle, which stated that certain pairs of physical properties, such as a particle's position and momentum, cannot both be known. According to quantum mechanics, nature itself imposes the limit. Then came an even stranger twist. In 1928, British physicist Paul Dirac combined quantum mechanics with Einstein's special relativity into what is now called the Dirac equation. Hidden within its mathematics was an astonishing prediction. Every particle should have an antimatter counterpart with the same mass but opposite charge. At the time, no one had ever seen such a particle. 4 years later, in 1932, American physicist Carl Anderson discovered the positron while studying cosmic rays at the California Institute of Technology. Yet even as the theory accumulated spectacular successes, its meaning became increasingly controversial. In 1926, Max Born proposed that Schrödinger's wave function did not describe a physical wave, but rather the probability of finding a particle in a particular state. This probabilistic interpretation profoundly disturbed Einstein, who believed nature must ultimately obey deterministic laws. His frustration became legendary. "God does not play dice," he famously declared. Bohr responded just as sharply, "Stop telling God what to do." At the center of the mystery lies what physicists call the measurement problem. Before a measurement, the mathematics describes multiple possible outcomes existing simultaneously in a quantum superposition. Yet the instant an observation is made, only one definite outcome appears. Why? No experiment has definitively answered that question. Instead, several competing interpretations attempt to explain it. For almost a century, quantum mechanics has become humanity's most successful scientific theory, and perhaps its least understood, Richard Feynman's crazy idea. By the late 1970s, quantum mechanics was facing a growing problem. As scientists attempted to simulate increasingly complex quantum systems on conventional computers, they ran into a mathematical wall. Every additional quantum particle dramatically increased the number of possible states that had to be calculated. A system with just 50 quantum particles could require tracking more than 1 quadrillion possible states. Nature handled these calculations effortlessly. Human computers did not. This is where the need for quantum computing was born. That realization crystallized in May 1981 at the first conference on the physics of computation held at the Massachusetts Institute of Technology in Cambridge, Massachusetts. Among the speakers was Nobel Prize-winning physicist Richard Feynman, already famous for his work in quantum electrodynamics and his unconventional way of thinking. During his keynote lecture, titled Simulating Physics with Computers, Feynman proposed an idea so radical that it would redefine an entire field. Instead of forcing classical computers to imitate quantum mechanics, why not build computers that obey quantum mechanics themselves? As he bluntly told the audience, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." This was a completely new way of thinking about computation. Feynman's challenge inspired physicists around the world, but one young theorist pushed the idea much further. In 1985, at the University of Oxford, David Deutsch published a landmark paper describing the first theoretical model of a universal quantum computer. Borrowing from Alan Turing's concept of a universal computing machine, Deutsch argued that a quantum computer could perform any computation that was physically possible, while also solving certain problems far more efficiently than classical machines. "Computers are physical objects," Deutsch would later write. "Computation is not an abstract mathematical process. It is a physical process." For nearly a decade, however, quantum computing remained an elegant idea, but nothing more than that. That changed overnight in 1994 when mathematician Peter Shor, then working at AT&T Bell Laboratories in New Jersey, unveiled what is now known as Shor's algorithm. It showed that a sufficiently powerful quantum computer could factor extremely large numbers exponentially faster than the best-known classical algorithms. This wasn't just another mathematical curiosity. Modern internet security, including the widely used RSA encryption system, relies on the practical difficulty of factoring massive integers. If a large fault-tolerant quantum computer could perform that task efficiently, much of the world's public key cryptography would eventually need to be replaced. Governments, intelligence agencies, and technology companies immediately recognized the implications. Quantum computing had suddenly become a matter of national security. The breakthroughs continued. In 1996, Love Grover, another Bell Labs researcher, introduced Grover's algorithm, demonstrating that quantum computers could also accelerate unstructured search problems with a quadratic speedup over classical methods. Unlike Shor's algorithm, which targeted a specific mathematical challenge, Grover's work suggested that quantum advantages might extend across a much broader range of applications, including optimization, machine learning, and database searches. By the end of the decade, quantum computing had evolved from an intriguing theoretical possibility into one of the most exciting frontiers in computer science. Then, reality intervened. Building a quantum computer proved far more difficult than designing one on paper. In 1998, separate research teams at the University of Oxford, IBM Almaden Research Center in California, the Massachusetts Institute of Technology, and the University of California, Berkeley, demonstrated some of the first working quantum bits, or qubits, using techniques such as nuclear magnetic resonance. They successfully manipulated systems containing only 2 or 3 qubits. It was an extraordinary proof of concept, but scaling from 3 qubits to thousands would prove unimaginably difficult. The greatest obstacle was something physicists call decoherence. Quantum states are extraordinarily fragile. Tiny vibrations, stray electromagnetic fields, microscopic temperature fluctuations, or even interactions with surrounding atoms can destroy a qubit's quantum information in fractions of a second. Every additional qubit made the engineering challenge even harder. The dream still existed, but nobody knew whether the universe itself would actually allow it. And just like that, the years marched on. The 30-year race. Nobody was watching. While the world was lining up for the first iPhone, binge-watching Netflix, and watching artificial intelligence slowly enter everyday life, another race was unfolding entirely out of public view. The competitors weren't just technology giants like IBM, Google, Microsoft, Intel, IonQ, Rigetti, and Psi Quantum. Governments joined the pursuit as well. China invested billions into quantum research. The United States passed the National Quantum Initiative Act in 2018, committing more than $1.2 billion to accelerate quantum technologies, and the European Union launched its €1 billion quantum flagship program the same year. Quietly, one of the largest scientific and technological competitions of the 21st century had begun. Despite the shared goal, no one agreed on how to reach it. IBM and Google largely bet on superconducting qubits, or tiny electrical circuits cooled to temperatures just above absolute zero, around 15 millikelvin, which is colder than deep space itself. IonQ pursued an entirely different strategy, trapping individual ytterbium ions with electromagnetic fields and manipulating them with lasers. Psi Quantum rejected both approaches, betting instead that photons, particles of light, would ultimately scale better. Companies such as Qujera and academic laboratories advanced neutral atom systems, arranging individual rubidium or cesium atoms into programmable arrays using optical tweezers. Microsoft pursued perhaps the most ambitious route of all, topological qubits based on elusive Majorana quasi-particles, hoping they would naturally resist errors. Every approach had strengths. Every approach faced formidable engineering challenges. Nobody knew which path would ultimately prevail. The reason was deceptively simple. Qubits are extraordinarily fragile, unlike classical computer bits, which reliably remain either a 0 or a 1. Qubits exist in delicate quantum superpositions that can be destroyed by almost anything. A tiny vibration in the laboratory, a stray electromagnetic pulse, slight imperfections in the surrounding materials, even high-energy cosmic rays arriving from outer space can flip quantum states or generate bursts of quasiparticles that disrupt superconducting circuits. Researchers had to battle sources of noise that conventional computer engineers rarely had to consider. Building a quantum computer became less like assembling electronic components and more like trying to balance thousands of spinning plates while someone constantly shook the table. As researchers increased the number of qubits, the challenge grew exponentially. Every additional qubit created new opportunities for unwanted interactions, calibration errors, and decoherence. Maintaining quantum coherence across dozens or eventually hundreds of qubits required astonishing precision in fabrication, cryogenics, microwave control, laser systems, and error characterization. Then, in October 2019, Google announced a breakthrough. Its 53-qubit superconducting processor, named Sycamore, had completed a specialized random circuit sampling task in approximately 200 seconds. According to Google's paper published in Nature, the same calculation would have taken Summit, then one of the world's fastest supercomputers, around 10,000 years. Google called the achievement quantum supremacy, a term coined years earlier by Caltech physicist John Preskill to describe the moment a quantum computer performs a task beyond the practical reach of classical machines. The celebration, however, lasted only days. IBM challenged Google's comparison, arguing that improved algorithms and optimized use of classical hardware could reduce the computation from thousands of years to roughly 2.5 days on a sufficiently configured supercomputer. Google's experiment remained a remarkable engineering achievement, but the disagreement revealed something important about science itself. Even historic breakthroughs invite scrutiny. Preskill himself cautioned against overinterpreting the result, emphasizing that quantum supremacy was not the end of the story, but the beginning. That realization shifted the entire field. Researchers increasingly understood that adding qubits alone would never be enough. A machine with 1 million unreliable qubits would still be practically useless. The real challenge was keeping quantum information alive long enough to perform meaningful computations. That meant developing sophisticated quantum error correction capable of detecting and repairing errors faster than they accumulated. It was no longer a race to build the largest processor or claim the fastest benchmark. But then again, Google impressed the world yet again. Google's Willow and the making of the future of physics and everything else. For more than 40 years, quantum computing had been haunted by a single question: whether anyone could actually build a machine that kept its quantum information alive long enough to perform useful calculations. Every prototype, every breakthrough, every record-breaking processor eventually collided with the same invisible enemy: errors. Then, on December 9, 2024, Google Quantum AI announced its newest quantum processor, Willow. At first glance, the chip didn't appear dramatically different from previous generations. It contained 105 superconducting physical qubits, roughly twice as many as Google's 53-qubit Sycamore processor that made headlines in 2019.
Google's Willow quantum chip just solved a problem that would take classical supercomputers longer than the age of the universe.
If raw qubit count were the only measure of progress, competitors had already built larger systems. IBM had unveiled processors with well over 100 qubits and was steadily expanding its hardware roadmap. The real breakthrough wasn't the number 105, it was what those qubits managed to accomplish together. Hartmut-Neven, the founder and head of Google Quantum AI, described the milestone in unusually direct language. Willow takes us significantly closer to running practical, commercially relevant algorithms that cannot be replicated on conventional computers. But even Neven emphasized that the real achievement wasn't raw computational speed. It was reliability. After decades of fighting quantum errors, Google's researchers had demonstrated something the field had pursued since the 1990s: evidence that quantum error correction could actually improve as systems became larger. To understand why that mattered, imagine trying to write an important message on paper while someone continuously shakes your arm. Every few seconds, another letter becomes distorted. Now imagine that every time you try to correct one mistake, you accidentally create two more. That was the reality facing quantum engineers. Unlike classical bits, which are remarkably stable, quantum bits, or qubits, are exquisitely sensitive to their environment. Even microscopic disturbances can alter their fragile quantum states. A tiny burst of heat, electrical interference, vibrations, manufacturing imperfections, stray magnetic fields, or even energetic particles from cosmic rays can introduce errors before a calculation is complete. The solution sounds deceptively simple: correct the errors. But quantum mechanics refuses to cooperate. In an ordinary computer, engineers can freely copy information, compare it with backups, and restore corrupted bits. Quantum information cannot be copied in the same way because of the no-cloning theorem, one of the fundamental principles of quantum mechanics. Instead, physicists had to invent an entirely new form of error correction, distributing the information from a single logical qubit across many physical qubits so that errors could be detected indirectly without destroying the computation itself. That distinction became the heart of Willow's achievement. A physical qubit is the actual hardware device, the tiny superconducting circuit fabricated on Google's chip. A logical qubit is something much more sophisticated. It is an error-protected quantum state built from many physical qubits working together as a team. In practical quantum computing, logical qubits, not physical ones, are what ultimately matter. A processor containing millions of unreliable physical qubits could still be useless if it cannot produce a small number of dependable logical qubits. For decades, this idea remained largely theoretical. Engineers found themselves trapped in a vicious cycle. For years, the field seemed trapped in a vicious cycle. Adding more qubits made quantum computers more powerful, but also dramatically more fragile. Every new qubit created additional opportunities for noise, interference, and errors. Some respected researchers openly questioned whether scalable, fault-tolerant quantum computing would ever become practical. Then came Willow. Google's researchers demonstrated that as they increased the size of their encoded logical qubits, the logical error rate actually fell instead of rising. This is known as below-threshold quantum error correction. This historic accomplishment, Google Quantum AI founder Hartmut-Neven wrote when announcing the results, is known in the field as below-threshold quantum error correction. This is one of the biggest engineering milestones since the idea of quantum error correction was first proposed. Willow also delivered another astonishing demonstration. In Google's benchmark test, the 105-qubit processor completed a specialized quantum computation in under 5 minutes. According to Google's estimate, one of today's fastest classical supercomputers would require roughly 10 septillion years. That's 10 followed by 24 zeros to perform the same task. For perspective, the observable universe is about 13.8 billion years old.
Would take the fastest supercomputer 10 to the 25 years. That's a 1 with 25 zeros following it, or a timescale way longer than the age of the universe.
Google is under no illusion that the journey is over. The company's long-term roadmap envisions scaling from today's hundreds of physical qubits to millions of physical qubits working together to create thousands of stable logical qubits. If that goal is achieved, quantum computers could simulate molecules with unprecedented accuracy, accelerating the discovery of new medicines, catalysts, fertilizers, batteries, and advanced materials. They could tackle optimization problems that challenge today's most powerful supercomputers and help scientists investigate questions at the frontiers of physics, from exotic quantum materials to black holes, and perhaps even quantum gravity itself. Meanwhile, IBM too has steadily scaled up its quantum processors, while emphasizing that the future depends not on bigger chips alone, but on better error correction and architectures capable of growing to millions of qubits. Microsoft is taking a riskier approach, pursuing exotic topological qubits based on Majorana zero modes, which could naturally resist errors if they can be reliably controlled. Meanwhile, companies like IonQ, PsiQuantum, and Q-Era are betting on trapped ions, photons, and neutral atoms, respectively. Although they disagree on the best hardware, they all share the same goal: building fault-tolerant quantum computers that could one day revolutionize the world we live in and change everything forever. But what does that mean for us, for our future as a species? What happens next? If Richard Feynman's vision of practical quantum computing is ultimately realized, many of the world's leading physicists believe that we would get much more than just wildly super-fast computers. One of the most optimistic voices is theoretical physicist Michio Kaku. For years, Kaku has argued that humanity is approaching what he calls the quantum age, a technological era following the industrial age, the electrical age, and the information age. He believes quantum computers could become extraordinary scientific tools rather than replacements for conventional computers.
We all know that digital computers changed virtually every aspect of our life. Well, the arrival of quantum computers could be even more historic than that.
He has suggested they may help scientists design entirely new molecules atom by atom, discover catalysts that dramatically reduce industrial energy consumption, accelerate the search for room temperature superconductors, improve battery chemistry, optimize fusion reactor materials, and shorten the time needed to develop life-saving medicines. Nature is quantum mechanical, Kaku often reminds audiences. So if you want to simulate nature, it makes sense to use a quantum computer. David Deutsch sees an even deeper implication. The Oxford physicist who first described the universal quantum computer in 1985 argues that computation is not something humans invented. It is woven into the fabric of physical reality itself. Computers are physical objects, Deutsch has written. The science of computation is therefore part of physics. Deutsch is also one of the strongest supporters of the many worlds interpretation, a theory proposed by physicist Hugh Everett III in 1957. According to this idea, quantum events don't force reality to choose a single outcome. Instead, every possible outcome continues in its own branch of reality. In this view, quantum computers work not because the wave function mysteriously collapses, but because quantum mechanics naturally allows many possibilities to evolve before producing a result. Many physicists disagree with that explanation, but its significance lies in the fact that quantum computing has revived philosophical questions once considered purely academic. Long before quantum computers existed, another visionary physicist proposed an even stranger idea. John Archibald Wheeler, who worked with both Niels Bohr and Albert Einstein, coined the phrase "it from bit." Wheeler suggested that information may be more fundamental than matter itself, that every particle, every field, even space-time, ultimately arises from acts of information. Every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from the apparatus elicited answers to yes or no questions, he wrote in 1989. At the time, the idea sounded almost philosophical. Today, information has become one of the central concepts in modern theoretical physics. MIT physicist Seth Lloyd pushed Wheeler's idea even further. In his 2006 book, Programming the Universe, Lloyd argued that the universe itself can be viewed as a giant quantum computer continuously processing information through every interaction between particles. His point was not that the cosmos is literally running software, but that quantum interactions naturally perform computations as physical processes unfold. Whether one accepts that framework or not, it illustrates how quantum computing has changed the questions physicists ask. Perhaps the biggest surprise of all is that quantum computing is no longer just influencing computer science. It may also be changing how physicists think about the universe itself. Over the past decade, researchers such as Juan Maldacena of the Institute for Advanced Study and Stanford physicist Leonard Susskind have discovered remarkable mathematical links between quantum information, quantum error correction, black holes, and even the fabric of space-time. These discoveries weren't expected. Scientists originally developed quantum error correction simply to protect fragile qubits from errors. Instead, they found that the same mathematics kept appearing in some of the deepest theories about gravity and the universe. One of the key ideas behind this connection is something called the holographic principle, proposed by Gerard T. Hooft and later expanded by Leonard Susskind in the 1990s. It suggests something almost unbelievable. Everything happening inside a three-dimensional region of space might be fully described by information stored on its two-dimensional boundary, much like a hologram creates the illusion of depth from a flat surface. In 1997, Juan Maldacena strengthened this idea by proposing the ADS-CFT correspondence, a mathematical framework showing that, under certain conditions, a theory containing gravity can be exactly equivalent to another theory without gravity living on its boundary. This model has become one of the most powerful tools in theoretical physics because it allows scientists to tackle problems about black holes and quantum gravity from an entirely new perspective. Then came an even stranger realization. Physicists discovered that the mathematics used to protect information inside a quantum computer closely resembles the mathematics that appears to describe how space-time itself might be held together. Some researchers now suspect that quantum entanglement, the mysterious connection that allows two particles to remain linked across vast distances, may also be the glue that gives space-time its structure. In other words, space itself may not be fundamental. It could emerge from deeper patterns of quantum information. If these ideas are correct, the implications are astonishing. Quantum computers may eventually become far more than powerful machines for chemistry or cryptography. They could become experimental laboratories for testing ideas about black holes, gravity, and perhaps even the earliest moments after the Big Bang. These questions have challenged physicists since Einstein. It's far too early to know where this research will lead, but few expected that a technology invented to process information would end up offering clues about the structure of reality itself. For the first time since Einstein began searching for a unified understanding of nature, the worlds of information and gravity may be starting to speak the same language. History rarely announces its turning points in advance. In 1874, Max Planck was told there was almost nothing left to discover in physics. 26 years later, he transformed humanity's understanding of reality. Today, engineers are no longer trying to understand quantum mechanics alone. They're learning to build with it. Whether Google's latest breakthrough becomes the transistor of the 21st century or simply another stepping stone, nobody can say. But history has taught us one thing with remarkable consistency. The moment we believe we've reached the end of science is often the moment the next revolution begins. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.